I'm feeling humbled. So just to begin with, give me a minute to share my screen. So just to save some bandwidth, I'm switching off my video. I'm sorry. Yeah. So first of all, I'm thankful to my fellow coordinators of this Asia Connect project, and also Professor Rajita Oja, who has given me a chance to get associated with this project. And today I'm here with the talk on the deep learning, deep neural network, and convolutional neural network. So if we begin with, then yeah. So if we talk about deep learning, so we can, every one of us knows, like this word has become a buzzword and daily we are talking about it. So deep learning today, basically we can say that artificial intelligence has penetrated practically every aspect of human life, right? We can see right from the assistant to Google Map to, I mean, even now this chat GPT. So, I mean, everywhere it has penetrated. And the main catalyst behind it is deep learning. So deep, we can say that actually deep learning is everywhere. And as you can see that here, some examples are being shown on this slide. We can see that we can use it for definitely computer vision is one of the area where it is being used heavily. So image classification, then speech recognition, language translation. I mean, so many areas there. Then as we are talking about these days, biomedical things like medicine and biology, so we are doing all sort of detection, like cancerous cells detection on let us say brain tumor, mammogram, so many this thing. Then this diabetic grading, I mean, apart from that, in media and entertainment also, there are so many uses of deep learning that is so the video captioning, video search, right, that is all possible with the deep learning. And security and defense, of course, surveillance has been benefited a lot. And the most important application which will attract the young minds present today, that is the autonomous vehicles, right? So how many of you are thinking of roaming in Tesla? So with this, so it is high time to learn to know what is deep learning basically. So as we all know that deep learning is a machine learning technique that actually allows computers to learn and improve their performance with experience and data. So it achieves great power and flexibility by learning how to represent the concept of the word as a nested hierarchy of concept. And here each concept is defined in terms of simpler concept. So now let us see this big picture first, AI, ML, and DL. So because this course is, as you know, AI, ML. So since day one, we started with AI. So we say that, okay, any technique that enables computers to mimic the human behavior. And then we talked about machine learning. So where we saw that how computers learn without explicitly program. And now after that, it is the turn of deep learning. So deep learning is nothing but actually a subset of machine learning, where we are making use of multi-layer neural network. Right? So neural network, you are already aware of now. So when we talk about AI, basically we can say that there are three paradigms of AI. One is your rule-based system, another is your classic machine learning, and then today we will talk about that is your representational learning, or you can say deep learning. So here let us talk about more about these machine learning system and why we landed up to deep learning system. So when we talk about machine learning system, and you are all are studying like a couple many times during this series also in this course, that okay, in the machine learning, if you see this picture here at the bottom, then we are extracting these handcrafted features, and then this then by using these features, we make a trainable system, and then we get the final output. But what are the issues with the approach, right? That forces us to move our attention. So here, just a minute. So if we talk about traditional machine learning, then we are using, as you can see here, handcrafted or manually designed features. Now, what are the issues with the handcrafted features? That they are often over-specified as well as incomplete. Right? And they are actually application dependent. So we cannot generalize it on the other applications. And it is like computing these handcrafted features that is time consuming also in terms of design and validation. Now, apart from that, we have another this thing that development, as I already told you, okay, yeah, it is a costly and complex job to design specific features. So if you look at the literature of the pattern recognition or machine learning, right, it is full of all sort of features. So a type of feature which is working good in one application may not be working well in the other applications. So apart from this, we have a problem, another problem with the traditional machine learning system, and that is the curse of dimensionality. Now, what is curse of dimensionality? If we have a fixed set of training images, so what happens if we increase the number of features? So in the beginning, what happens that performance of the classifier increases. But if we increase it further, then it increases only up to a point, and then it starts decreases. Okay? So with these, let us see what are deep learning systems. So if we just compare the two, machine learning and deep learning systems, so like this is the same thing. You can say, okay, the manual task we are using to develop feature extractor and extracting features, and then the automated training is there. So traditional machine vision techniques, they begin with a top-down approach. And so top-down prescription of components, you can say that constitute the image as its features, right? And deep learning models, if you say on the other hand, that is basically we say end-to-end learning, means that deep learning models actually flips this entire process on its head, I must say that. And the deep neural network training process uses massive data sets and countless training cycles to teach the machine from the bottom up, right? In place of top down, now here it is bottom up. So how a cat looks basically. So during the training process, the algorithm automatically extract the relevant features and of cats. Let us say when we will present different images of cats, so it will learn the relevant features of cats in general, and this process will produce basically a model, right, that can be applied to previously unseen images of cat, let us say, to produce an accurate classification to image. That is what is there with the deep learning and machine learning. Now when we say that so with this we come to the deep learning. So here you can see that hierarchy of features. So deep learning actually learns a rich hierarchical representation automatically by extracting features at different levels. So you can see that here low level features, mid level features, high level features, right? That is how. So basically this provides you a flexible learning framework, and here you can our trained algorithm may work for a broad range of problems, right? Or classification, segmentation, object detection, like to name a few in the computer vision. Similarly, in other areas also, like speech and this natural language processing and all. So when we say that learning hierarchy of feature extractor, then our goal is basically to learn the useful higher level features from the images. So here we can say that, let us see again the same another picture but depicting the same thing. So here what is the beauty of this architecture, that we are starting from the pixel and we are ending at the object. So we can say that we started from the pixels, then first layer we are giving, that is low level features, we are getting the edges, then we are getting the mid level features, that is we are identifying some object parts, and finally at the high level we are going to identify the objects, right? So here each layer of hierarchy extract features from the output of the previous layer, right? So you can see that each layer here is extracting features from the output of the previous layer. And here the layers have, I mean, usually they have the nearly similar structure, and they are trained jointly. Okay. And so here, if we talk about this, then we need actually a function, right? We talked about machine learning, you know about that, you are learning a classification function. So here a function to map the pixels to the objects, right from the pixels to the object is definitely a complicated task. And the series of hidden layers extract increasingly abstract features. That is what we saw, increasingly abstract features. So the first layer edges, then object parts, then finally objects, right? And then the final decision is made by a simple classifier. So when we talk about deep learning ingredients, then first ingredient you are now familiar with, that is your artificial neural network, which is a learning machine here. And we know now that artificial neural network, they are based on the concept of perceptron, which are the basically the basic building blocks for deep learning. Now the second thing is data, right? We need huge amount of data so that our model may be generalized. Then we need specialized algorithms to train this artificial neural network, how to keep these losses, how to optimize your loss function so that you can get a better function over there, right? And finally, we need the computing resources. Okay, previous slide, somebody is saying previous slide, just a minute. Yeah, this slide you were talking about. Okay, so Kumar, this is what we are doing in the deep learning. Basically, we are learning a hierarchy of feature extractors. So we can say that we are learning higher level features from the images. How? So see, if you talk about a picture, what we have in a picture, we have only pixel information, right? For example, if you take any picture over there, we just have this raw pixel data, right? That let us say I'm saying, okay, my image is a 256 cross 256 image. And then, so we have intensity value of each of these pixels, right? That is the data we have. Now, by using that data, any picture, right? You talk about any picture. So if you are familiar with the images are a 2D array of intensity values. So if you see any picture there, we have the basic element is, so we will talk about textual data also, but here this time, our focus is on this image data, right? So here we are having these pixels, and then from those pixels we are learning the higher level object, which is not obviously a easy task. So we are learning these things in a layer wise manner. And so at the first layer, we are just talking about the low level features. For example, here we saw the edges. Then we move to as we move to the higher levels, we are learning more high level features, right? Or abstract features over there. So so what is happening here? We are having layers of hierarchy, and where each layer learns extract features from the output of the previous layer, and these layers are being trained jointly. So that is what is your deep learning. So what is there in the deep learning? As I was talking about, it is first of all, we need artificial neural network as a learning machine. Then we need data, huge data. Then the specialized algorithms to train these artificial neural network. And finally, we can say that computing resources, because now you see that the many hidden layers, right? How to process, how to optimize the loss and all those things. So here, with this, so you are already aware with the neural network, and now let us talk about deep neural network. So when we say that deep neural network, again, you are having, okay, this input layer and the output layer. Then please bear, I mean, if you have any question, then drop a message, right? Because I see it flashes, then my attention goes there only. So if there is any question, then please write there. So here we can say that from input to output, we are having this many layers, right? So deep neural networks have many hidden layers, and when we are having many hidden layers, then potentially we are having millions of parameters, right? So if you talk about dense layers, let us say fully connected layers, we just you are already gone through the multi-layer perceptron, and where what happens that each neuron you can see is connected to all neurons in the succeeding layer, right? So the term deep comes from the more, you can say, the larger number of layers, hidden layers. So why do we need deep neural networks? That is another question. So if we talk about universality theorem, then basically the representational power, then we say that any continuous function, right? You can see this function can be realized by a network with just one hidden layer, right? So you say, okay, I will not go into the detail of that. You can refer this. So you can say that, okay, this is a network with just one hidden layer in between, right? So, but remember when it will work well, when your hidden layer is having enough number of neurons, right? And so the question comes that when we can do things with just one layer, then why do we want to go for a deep neural network when we can work with fat neural network, right? So remember that here the neural network use non-linear mapping of the input to the output, right, to compute the decision boundaries. Okay. So first of all, we will try to find out this question that why do we use neural networks, deep neural networks, right? And then we will move towards the CNN, convolutional neural network. So when we talk about this two network are being shown on this slide. The first one is your shallow network and the second one is your deep network, right? So whether we should go for a fat and short network or thin or a tall network. Now, let us say I'm saying that both of these network, right, irrespective of they are fat or thin, they are using the same number of parameters, right? So when they are having same number of parameters, then which one is better, right? Why go for deep? So remember that the fact that deep neural networks work better is an empirical observation. If we talk mathematically, I just showed you previous slide, the universality theorem. So if we talk mathematically, then deep neural networks have the same representational power as a one layer neural network, right? So in one layer model, the layer might be massive and then the network is prone to overfitting the data. And therefore, it is common trend in the research community that network architectures need to be deep. So deeper versus shallow network here, deeper we know that, okay, so I just told you that, okay, deeper network perform better than the shallow network, but again, there is a limit. So after a certain number of layers, the performance of deeper networks plateaus, right? So it will not go up that way. So we'll see why it happens. So first of all, we'll see that why this deep learning is useful, so that we should go for it. Remember that, as we just saw, deep learning provides us a flexible and learnable framework so that we can represent visual data, text data, speech data, linguistic information, right? And this neural network, they can be learned in unsupervised as well as supervised manner. And so, as I showed you in the previous slide, I mean, when I compared machine learning and deep learning, that deep learning is an effective end-to-end system learning, but definitely it requires a large amount of data. And what happens is that this is a fact known to most of you, that since about 2010, deep learning has outperformed other machine learning approach, right? First so initially like vision and speech, later on, a lot of work in natural language processing and other applications also. But what was happening since 2010? So why this boom came in 2010, right? Because if you talk about, they are based on the this MLP, so a multi-layer perceptron. So these perceptrons are known to us since long back, right? 1950s. Then the neural networks came in 1980s, right? We are knowing what is back propagation, and we are knowing what is the gradient descent, what are the methods to optimize gradient descent. Then why this took so much time that in 2010 we say that, okay, now it is the age of deep learning. So let us first see what was happening, right? Why this slowdown happens between 1992 to 2006. So as I told you that theoretically, accuracy of approximation increases if the number of layers increase, right? But practically it is not feasible, right? Why? Because there are many factors responsible for this. One factor is that there is limitation with the processing power. Then when we are training this multi-layer perceptrons, then accuracy didn't improve with more layers. Then we are not having enough data for training multi-layer perceptrons. So that because of that, we are having these generalization errors. And apart from that, there is another important problem, that is the problem of vanishing gradient. So while you just saw in the last two lectures, right, how to learn the neural network, and when while neural networks are being learning, then we need to multiply several gradient values, right? And now those gradients values may be less than one also. So what happens for when we go for deep neural networks, and therefore these gradient values, they are already less than one, and they will go on lesser than one, right, like that, and ultimately what will happen, they will vanish. And once this gradient becomes so small that like that it vanishes, then it leaves actually no scope of improvements in the training through back propagation. So you'll say that in fact your neural network will die. So this was the problem. Now, so what is the, so before knowing about, before talking about the solution, let us just revise what you have learned yesterday. So if you remember the gradient descent, right? So neural network, they are actually being trained using iterative gradient based optimization process. And so you get a solution which results in a cost function with a very low value, right? Low cost. So when we apply gradient-based learning, it is very much important to choose appropriate cost function. Now, if we just see this gradient descent, this error surface is being drawn here, and let us just assume that we are having only two parameters, W1 and W2 in the network. Then what happens here? This is, so we need to identify these parameters, and here the colors are representing the value of cost, or you can say loss functions, right? So ultimately, we need to reach at the global minima, right? This is the minimum value here of this cost for these two parameters, and we need to reach that. Now, how to reach there? So for reaching there, what we do, we randomly pick a starting point, right? So we have just picked, okay, this is my W1 and this is my W2. Now what will happen? We need to compute the gradient and this negative gradient, right? So we are going to compute the negative gradient at this starting point. Then we are going to multiply it with the, so this is the computation of gradient, and then we are going to multiply it with the learning rate, right? Now, once we do it, then what happens that we get the next value, right? So that is again what will happen, as I told you that this is an iterative process. Now we will do the same thing here at this point, right? When we are again going to calculate this, compute this negative gradient at θ1, and again multiply it with the learning rate, and that will give me this next point, that is θ2. Now, the same thing, we are going to apply this cost computing this negative gradient at θ2, and again, we are going to multiply it with learning rate, and we'll get the next point. And eventually, what we consider that eventually we would reach a minima, right? Now, but what is the problem with this approach? Your gradient descent algorithm stops. I mean, it never guarantees, your gradient descent never guarantees that you are going to reach at the global minimum, right? It will stop here. You can see that this is your global minimum, but this is your local minimum. So what happens that your gradient descent algorithm will stop when a local minimum, right? Here you can see that this is an arbitrary surface. So it will stop at the local minimum of the loss surface, right? So however, when we go through the studies, we know that, and that is why it is being used also, that gradient descent work well for the neural networks. Now, if we just see more about, if we talk more about this, that local minima, so you can see that this is the surface, right? This is the loss surface, let us say, or cost this thing. So again, we are choosing just two parameters. So as Dr. Partha Pratimra was telling you that it is, I mean, plotting it with more number of parameters, it is so difficult. And you can see that for most of the task, the loss surface is highly complex. You can see that with only two variables, it is so complex, right? And it is also non-convex. So what happens that when we do this random initialization in the neural network, that results in a different initial points, right? So sometime when you are going for this random initialization, you are going to get a different initial parameters, right? And it means that every time you will choose a different initial point, you are going to reach a different minima, right? So you'll get the different results and you are reaching at, you can see here so many local minimas are there, right? So your gradient descent may reach to different minima at every run, right? And therefore, neural network will produce different predicted output, right? Now, what is the problem? Problem is that currently we don't have an algorithm that guarantees that we will be reaching a global minimum for an arbitrary loss function, right? And beside this local minima problem, right, there are other problems also. Let us see with the gradient descent that okay, so so this is what we talked about, that it will stuck up, let us say, at local minima. Apart from that, the gradient descent algorithm can be very slow at plateaus, right? And see here, and it can get stuck at the saddle point also. So these are all problems with the this gradient descent approach. Now come to the vanishing gradient problem. Now, as I told you that it is a deeper network, let us say, and so if the gradient values are very small, so then our network is going to learn in a very slow manner, right? So when there are more number of layers in the network, the value of the product of derivative, remember back propagation and all, we are making use of the this derivatives, right? So while training, the gradient can become either very small, both problems are there. Either it is going to be very small, that we are calling vanishing gradient, or it may become very large, that is exploding gradients, right? So both sort of problems are there. So let us talk about vanishing gradient now. So when there are more number of layers in the network, the value of the product of derivatives decreases, right? Until at some point, the partial derivative of the loss function approaches a value which is very close to zero, right? And then, so this is what we say, that when your partial derivative value goes to very close to zero, we say that the partial derivative vanishes, right? And we call it vanishing gradient problem. So vanishing gradient problem, we can say that either your network is going to learn in a very slow manner, or it is, in some cases, it is not at all learning, right? So probability of the problem of vanishing gradient eventually leads to the death of the network, right? And vanishing gradient problem arises from the basically nature of the partial derivative of the activation function, which are used to create the neural network. And so what happens that I mean, you did yesterday also that sigmoid function, right? So sigmoid function is one of the most popular activation function, which is used to develop neural networks. And what is the problem of the vanishing gradient? That it becomes worse when you are using sigmoid activation function, right? Because you know that it goes less and less, and ultimately it vanishes, right? So what is the solution here to deal with the vanishing gradient problems, right? So one solution is that you change your by the death of network means that now my network is no more learning. So we are we are going through the process, but my network is not at all learning, because the gradient is becoming so close to zero, it vanishes. And see, the back propagation and all, we are making use of gradients, right, to train our model. So here, so what is the one solution? Maybe that we change our activation function, and then we are saying, okay, so after sigmoid, today when we will talk about CNN, I will tell you about the ReLU activation function. And then some other techniques are also being used, regularization, this batch processing, mini batch processing, then this dropouts, all those things. But there is another thing which can be used. That is that how we can find out another way so that our deep networks may perform better and fast. So what is the way to it? And so Hinton et al., they gave in 2006, actually, they gave this concept. And not only Hinton, like at the same time, several different contemporary groups were working on the problem, and they gave this sort of solution in a different form. That so what they said, that okay, when we are having these multiple hidden layers, then the connection will be made between layers and not between the units within each layer, right? And what is happening? These layers will be trained on a set of examples without supervision. And our deep belief network can learn probabilistically to how to reconstruct its input, right? So the layers will be acting as a feature detector, right? And once your deep belief network is trained, then it is ready to perform the classification. And this change, right? All these changes which I will talk about previous, and now this how to change the way to train deep network. This actually led the development of the deep neural network as a powerful tool to solve the challenging problems, right? Many challenging problems. Object detection is one of them, speech recognition. So what we do in the deep belief network, we say that, okay, new training method. So we are going to train this layer wise, right? So we say, okay, train this layer first, then train this layer, then this layer, then this layer, and finally this layer, right? So what we did here, each of these non-output layer, these, right, they are trained to be an autoencoder, right? So we'll talk about more in the autoencoder in the tomorrow's lecture. And so right now you may, bear with it. So each layer here is made up of, is made to learn good features that are, which are received from the previous layer, right? So apart from this, another change came into the, in this training process, how to deal with the vanishing gradient problem. That 2015, actually the deep neural network, which actually started to came, that is why we say that 2010 it begins, but it's still like the actual deeper network, like with more than 150 layers, that ResNet came in 2015. So what they say that, okay, it is very much possible to train much deeper network. Now, what is the solution being suggested here in ResNet? We will again talk about it tomorrow in more detail. So we'll say that, okay, they make use of these skip connection, right? So skip connection, this is your plain block, and this is the block with the skip connection. We call it residual block, right? So skip connection, what is happening here? You can see that this input, right? So this residual block make it actually easier to for the layers to learn an identity function. So what happens here? We are going to add this input here to the output layer, right? So that we do not want our gradient to vanish. And what are the two benefit of this? That first of all, this definitely it is dealing with the issue of vanishing gradient, because we have set up an alternate shortcut here for the gradient to pass through. And another thing is that the model, they become enabled to learn an identity function, right? So that here, the problem which we are talking about, that the network is not learning at all, that problem is will not occur, so that the higher level layers of the model do not perform any worse than the lower layers, right? So now we can, before I begin to jump to the CNN, just maybe for a couple of minutes, this, so what is so with these developments, now our deep learning things, models become success, right? So what is the success mantra for deep learning models? The new algorithms came, then the computing power by that time, because earlier I still remember that when I used to worked upon this content-based semantic retrieval in 2010, then we have trained our model, right, machine learning, this on, because we are also working on the image on several machines. So what happens that initially CPU comes, then bunch of CPU we have used, and then GPU came, and now we are having high performance computing. That is the multiple GPUs are available to you. So with the so how this success was possible, how the deep neural networks came into the picture with the increased availability of data, significant improvement in the computing power, increased model size, because we have learned how to mitigate the problems in training the deeper networks, right? And we got this new ways of learning representations, and now our models are generalized well, and they become flexible so that we can use them for a broad range of tasks. So when we talk about deep neural network architecture, then these are all, there are like conventional neural networks are there, then convolutional neural network, recurrent, right? You will learn many of these in this in the remaining days. But today our focus is on convolutional neural network. So what is a convolutional neural network? It is a class of uh, deep neural network that is most commonly applied to analyze visual imagery. See what happens since this CNN came, and since then the researchers were trying to use, neural network came, researchers were trying to use it on the visual data. And basically, after this, it is possible the field of computer vision has, grown beyond, you can say, limit. So, so this is possible. Like after when we have started using these deep neural network, that is in the form of CNN, to analyze our visual data. So before we go to the CNN, let us just understand what is the background of CNN. So I have already told you that why this, why this deep learning came forefront on 2010 onwards, why not before? Because again, if you talk about CNN, then this Lenet 5, right? This Leacon gave this model, and long back, 1998 only, right? That was the first example of applying back propagation and gradient based learning to train CNN, and it worked well for document recognition. And so it actually performed good job of recognizing digits of the zip code, right? So that is being used for zip code recognition in the postal services. So not in India, but abroad, like US, their postal services, they have used many such systems, so that based on the zip code, the automatically the letters may be put in the separate boxes. It becomes easy to separate them. But what happens beyond this? It was, scaling this. It was found to be difficult, and that is why there was so much gap there, because digits were relatively simple and limited set to recognize, right? And then came this LXNet in 2012. So a group of researchers from the University of Toronto, they actually developed an AI model that surpassed the best image recognition algorithms at that time, and that too by a big margin. So here, this is we can say that Alex Krzyzewski in 2012, he gave the modern incarnation of convolutional neural network, right? So now they were scaled. We saw that they are scaled now to be a larger and deeper, and they are able to take the advantage of the large amount of data that is now at this time. The large amount of data was available in the form of web images in the ImageNet data set, and now we see that convolutional neural networks are used everywhere, not only in image retrieval, object detection, segmentation, localization, all those things. So now with this, before we move, let me tell you the another this thing, because all these things are linked together. How this, especially because my area is computer vision, so I will talk from the vision point of view, imagery point of view. That at the meanwhile, this ImageNet, I don't know if you're aware or not. If not, then please search it. Right. So ImageNet was a data set, right? Large visual data set which contains more than 15 million of labeled high resolution images, right, of 22,000 categories. So let us say if you go for even for an animal, dog, cat, a very deeper, yes you can, so it is you can okay, it breaks the chain of thought. Yeah. So it is a very much the data arranged in the hierarchical manner. So if you go to any category, there are various subcategories there, and in fact later on people try to mimic to beat it, then also they were not able, right? So what classification has been done. So this idea actually was conceived by Professor Fefili, and so this ImageNet data set was so it's a it was a lot of work is being done when the images are being outsourced. There, the people have done this classification, and finally the data set was being launched in 2009. And then this is a very high quality data set, and it is highly popular among the researchers to test their image classification, as well as, I mean, all sort of tasks, object detection, object localization, all sort of tasks can be done. So what happens is that they launch a challenge, right? So the recognition challenge was being launched, and and for that recognition challenge, they use a very small portion of ImageNet in 2010 it started until 2017. So regularly every year, this competition was being floated. So on a smaller portion of ImageNet, that is consisting of only 1,000 categories, right? And so total count of training images was about 1.3 million. So they used to give the training images, they used to give the validation images, they used to give the testing image, right? And how the performance is calculated? Performance is calculated on the basis of top 1 and top 5 error rates achievers, right? So top 5 error rate, what is the meaning of this? This top 5 error rate, basically the percentage of images, right, where the correct label is not one of the model's 5 most likely labels. So the model will give corresponding to a picture, the model will give the most likely labels. So if the actual label lies within this first 5, okay, otherwise it is an error, right? So an interesting thing happened if you look at here, and that is what we're talking about, this LXNet and ResNet. So you can see that when we go for the classification, like when this top 5 error, then in 2012, when LXNet came, then it actually, before that, shallow models were there, or the state of the art classification methods based on the features, bag of features models, which are very popular at that time. Those things were there. And when the LXNet came, then you can see that these are the top 5 errors are being shown here on the, yeah, top 5 errors, right? So around 85% was the accuracy it gave. And as I told you, that not only high accuracy, but much higher as compared to the techniques of that time. So the conventional computer vision, like classification technique, they got it around 74%, and this gives you 85%. So a huge difference was there. But here also you can see that 8 layers. And tomorrow, when I will take CNN architectures, then I will tell you that how difficult it was to train this model. The model was trained on different GPUs. Now, after that, the people started working. One VGG came, which is also a very good network, and Google Net. But the actual deep neural network, we say that more than 150 layers, that is your ResNet, right? So now it has opened up a new field, right? So you'll say that most of the models are being inspired from these VGG ResNet, right? So this was there. Now, with this introduction, we can say that this discussion on the deep neural network, now we are ready to talk about the CNN in the visual data, right? So here, let us talk about neural network for image data, right? So let us say your input vector is an image, right? So, and we need to classify, let us say the 2 images are there, and we need to classify whether these images contain this bird or not, right? So let us say these 2 pictures are 256 cross 256 images, right? So 256 cross 256 pixels are there. So, and you know that in the, what I told you in the deep learning, in the, so pixels, all pixels, that is our input, right? So these inputs are given to your, these pixels are given as input to your input layer. So what will be the size of your input layer? This 256 cross 256, right? So it will come more than 60,000. Now, let us say here we have shown only one hidden unit, but when we're talking about deep neural network, so let us say our deep neural network is having 1024 units. So when we are having this 1024 units, then just imagine how many weight parameters your network is supposed to learn. This 256 cross 256 cross 1024, right? So too many. Right. So you can understand learning network, so many parameters, right? But let us look at the image data and see whether some heuristics can play a role in deciding our strategy to move on. So if we just look, these are the pixel intensity values for a block of an image. So let us say if you just take just one portion of the image, these are the intensity values over there, right? Now here you can see that when we talk about images, it is a high dimensional data, right? No, so large size images are there, and then the number of bits per pixel that way. So one thing is that they are having high dimensional data, but another point is there that this data is having redundancies. You can see that repeated, right? Similarly, this data is having patterns there, right? So you can see that these are some patterns over there, right? And these patterns actually repeat depending upon the uh, content of the picture, right? So so now, because we are looking for a smaller network, let us say what we can reduce the number of parameters to be learned so that in our deep neural network, right? So then the convolutional neural network came, and what was the main question that when we know, because still now you are aware with the fully connected model. So this is your fully connected model where each each neuron in the this layer is connected with each neuron of the next layer, right? So the question came that whether we need all edges in this fully connected model. And the second question is that can some of the weights be shared? So with these questions in the mind, we got the answer. The answer in the form of convolutional neural network, which are just neural networks with 3D activations and weight sharing. So you'll see that what do we mean by 3D activations and weight sharing. So when we go for images, then we need to basically what we do in the computer vision, we try to understand the image. We try to analyze the image, right? So now we need to learn patterns, right, which are very small as compared to your image size. For example, this is your image, and from this image, we want to learn a very small pattern that is, let us say, for eye, right? So we can say that now you know that those who are working in the area of image processing, they know that, okay, we use filters, right, to filters as a template to search that pattern in the picture. So let us say we are having a filter for this, which is nothing but my eye detector. So I have developed a filter, let us say, to detect this eye. And what we'll do is that instead of this instead of this entire weight parameter matrix, what we'll do, we will consider this small pattern detector, right? So the small pattern detector means that a small number of weights, right? Not the entire weight parameter matrix I need. And another good point was that same pattern, it is not like that when you developed a pattern, like a filter for a pattern, that pattern is present only one place in the picture. It is very much possible that the same pattern can be repeated, can be present at different positions in the image. For example, here you say that eyes, right? So you have developed that filter. Now you are finding, using that filter, you are finding this pattern present at various places in the picture, right? So same pattern detector can move around and it may detect eyes at different positions. So now what is convolutional neural network? Just look at it and then we will go into the working of it. So basically it uses parameter sharing, and here it makes use of the small pattern detectors, which we call as filter. And these filters are used to convolve over the entire image, right? And so what we do in the convolutional neural network, basically in this training process, because you know that we are learning weights, and here what we learn, here we learn these filters, right? So this filter, let us say you decide, we are saying, okay, eye filter, okay? So you decide this filter with some random parameters. Now you will do the forward and backward this propagation, and finally you will learn the coefficients of the filter which are corresponding to the eye detector, right? So the learning is in the similar way as you do it in the fully connected networks, forward pass, backward pass. But here we are going to remember always that this question that, okay, what we learn in CNN, we learn filters, okay? So just like we are having hidden layers in fully connected layer, here in the convolution in a network, we have convolution layers, right? And also because images are large size data. So just to handle the large size image data, we introduce pooling layers, right? So now our task is to understand what do we mean by these convolution layers, what are these pooling layers, right? All these things, okay? So first of all, let us start with convolution, because I'm not aware, I do not know how many of you are aware with this. So convolution with the image block. So here you can see that this is your picture and this is your filter. See, a small filter, right, as compared to this image. Now what happens that this filter is going to convolve with an image block. For example, if you place this, imagine that this filter is placed over here, right? This filter is placed over here. So and then what we are going to do, we are going to perform this multiplication followed by addition. So let us say when you are going to impose this filter over here, corresponding to 3 we have -1, corresponding to 0 we have 0, corresponding to 1 we have 1, corresponding to 2 we have -2, and so on and so forth. So what we'll do is that we are going to multiply the corresponding terms and then we will add it, and that will give me a number, right? And what we'll do, that number we will be writing in the output image, right? Convolved image, or you can say destination pixel. And this value, this number where you are going to write, you are going to write it for the center pixel. So usually what we do is that deliberately these filter, right, these filters are taken of odd sizes so that we can get a clear center, right? So whichever pixel we are placing this center, right, the response is generated for that pixel. For example, if I place this filter here, right, so again I will get a response, but this time this response will be corresponding to this pixel. Similarly, if I place this filter here, then what will happen, this will again give me a response, but that response I need to write for this pixel, right, center pixel. So this is the basic convolution operation. Now what we do is that when we slide this filter over the entire array, like, so first you, just a minute, okay, so first you place it here. Now let us just move it one place forward, right? So now again it will give me a number, but that number will be corresponding to this block, right, for this 2, right? So again this 0 will be multiplied with -1, 1 will be multiplied with 0, and so we do all the 9 multiplication, add it, and the whatever number we'll get, that number will come here, right? So again we are going to do this shifting, right? So we are going to basically shift this filter over this entire picture, and that is how we will generate this output, which we say that convolved image, right? So image convolution. So now what we will have in a convolutional layer, basically we will have a number of filters that are going to perform the convolution operation. So each filter, for example, here we have eye detector, right? So we will be in each convolution layer, what will happen? We will be having a set of filters. Let us say one filter is for your eye detector, another filter is for your nose detector, another filter is for your eyebrow detector, another filter is for your let us say lips detector, jaw detector, like that, right? So a convolutional layer is going to have a number of filters, and with each filter we are going to perform the convolution operation to the input. Now let us once again, whatever process I told you, the same process is given here. Okay, let us say this is your picture, this is your filter. Now how do you generate the output? So you can see here, first of all, so you are placing your filter so that the entire filter, right, is within this image, right? So we are not placing it like center of the filter, like center of the filter, putting it here at one, right? So when we will place center of the filter here, then only my entire filter is there within the picture, right? Now when you have placed this, then what will happen? As I told you, the corresponding terms are going to be multiplied, right? So 5 we will multiply with 1, 1 will be multiplied with 0, 7 will be multiplied with -1, and so on and so forth, right? And then so we'll do all these 9 multiplication, and we are going to add it, and finally, and when we are going to add it, we are going to get a number, and that, now in this case by chance we are getting the same, but in the output image, this number will be written in place of this center pixel, right? So this place, this generated value will be written. Now, how we are going to implement it? So just see here, we are going to convert the image block as well as filter in a single column vector. You can see that, okay, this is my X here. See this 5177, 25535. And this is my weights 10 minus 1 like that. And what we are going to do, we are going to calculate their dot product. See, we are talking about this since, last couple of lectures. So WT X, right? So that will give me this response. Okay. Now what we'll do, we are going to slide this filter. So we have, see, earlier my filter was here, right? So my center was at 2. Now when I will move it 1 pixel forward, so next my filter center will be at 5. So now you can see that my filter center is at 5. And again, I will do the corresponding multiplication. You can see that 1 is multiplied with 1, 7 is multiplied with 0, this 5 is multiplied with 0, this 0. 3 is multiplied with 1 and like, right? So 9 multiplication and then addition. So the response is generated here, that is minus 70. So in the output image corresponding to this pixel 5, the response will be this minus 70, right? And so we are going to slide it this way. So again, a new response will be generated and this process will continue till, so we go from, see, left to right, top to bottom. So when we talk about image, the processing method is left to right, top to bottom. So you are saying, okay, you are moving here. Now you will move this and then you are going to move 1 pixel downwards, right? And again, left to right. Okay, this is the process. So I hope this process, convolution process, is clear to everyone. If not, please let me know. So now the question comes that how we are going to perform the convolution on the RGB image, right? Because color images are having 3 channels, R channel, red, blue, and green channel. So here, remember that what we'll do, we will have 3 copies of our filter also, right? The same, like, but 3 copies. So here you can see, because your picture is having 3 planes. So we are having 3 copies of the same filter, right? Now what we are going to do, see, we are going to apply the convolution operation on each channel. Okay. So, so 1 cross 1, basically, you are just putting it on a pixel and multiplying it, right? So usually the just size which we take, that is your in the beginning here. 3 cross 3, 5 cross 5. Similarly, when you are taking 1 cross 1, then you are placing it there and then you are going to get the value. So we will talk about this also. So now here we are going to make 3 copies of the filter and we will apply convolution operation on each channel, right? And so what we'll get for each channel, we will, so corresponding to a position, what will happen? Let us say this is my R plane, understand it like this. This is my R plane, this is my G plane, and this is my blue plane, right? So 3 planes are there, okay? Now, so these are the 3 copies of the filter. What I will do, I need to convolve this R image with this filter, right? And we will get, so what is happening when we are placing this filter over there, we will generate a value. So this value is corresponding to this pixel, right? So we will generate a output. So this is the output corresponding to this image. And don't worry about this stride, I will talk about it later. So here, okay, I will come on that. So how do we deal with the corners? Just wait for a couple of minutes. So then we are going to apply this okay, with the, again, this filter with the G, and again we are getting the response. So we are getting the responses here, and then this bias. Okay, now add the 3, and that is how we are going to get the final. So for this pixel, you can see here 2, then 1, so 3 plus, let us say, 1 is bias. So at this position you are getting this 4. Similarly, you will get this similarly, we will get this for other pixels also, right? So, so that is what we are going to do with the RGB image. Now, so weight and multiply with the pixels values and then bias. So we can say that filter coefficients are the weights here. Okay. So now let us come back to our discussion, that is what is convolution layer. So when we talk about an image, then we are having, an image is having 3 channels. So let us say this is a small 32 cross 32 image with 3 channels. So this is my image and my filter is 5 cross 5, right? So now remember that this is called the depth of the image, right? So this because there are 3 channels, the depth is 3 here in the beginning. So we need to extend the filter also. So remember that filter will be extended to the full depth of the input volume. So we will get basically, what does it mean? We will get 3 copies of the filter, you can say, right? And we are going to, what does it mean? We are going to convolve the filter with the image, right? So let us say we are placing, your filter is being placed here. So what will happen? This will generate one number there, right? So you know how I just showed you the previous slide. So R corresponding to R channel, blue channel, green, or any one of the channels. So corresponding to each channel, you will generate a response for a particular pixel, and then adding this, that is how you will get the response for, let us say this is for the center pixel, you got this response, right? Now, so by this, what will happen when you will generate this response? This we say that this is a hidden neuron in the next layer. Now, what will happen when we are going to apply this? Because we need to translate this filter, right, on this entire picture, and that is how we will generate output of one filter, right? Now, as I told you that convolutional layer, we are having many filters, right? So each filter will give you one output layer, right? So this is your input depth, remember, and let us say we have used 10 filters here. So what it will give me? It will give me 10 outputs, right? So what will be my output depth? Output depth will be 10, because I will get, similar to this, I will get basically 10 response, right? 10 planes response I will get corresponding to each of these filters, right? So here to get this, that is why we say that 3D activations, right? So to get the 3D output of this depth D, we are using D different filters, right? And in practice, your convolutional neural network use many filters, right? As you can see here, 64 to 1024. So because what happens here, you see that this filter, right? So the filter is having that coefficient, and same filter is moved across the image. It means that we are the and filter coefficient and whenever we are placing this filter somewhere in the image, those pixels are the corresponding pixels are multiplied with the corresponding weights, right? So it means that when we are moving it from one set of pixels to the other set of pixels, we are giving those next set of pixels the same weight, right? The same filter coefficient, right? So with weight sharing, this process is called, this is convolution, okay? So just see the concept of weight sharing. Let us say this is your picture. So arrange it in a 1D manner, right? And so what happens here? So these colors are denoting the weights, okay? So let us say we are having this 3x3 filter, okay? 3x3 filter 9. So you can see these different colors, 9 colors, you can consider it corresponding to coefficient, right? So you can see that these coefficients are going to get values over there. See, we are not going to decide filter values. We are, in the beginning, we just choose any random values. That is what I'm telling you, that in convolutional neural network, we learn the filter coefficient. So in the beginning, I don't know, right? Yes, we will apply. Just let me give you some basics, and we'll come on these questions, right? So what happens here? You can see that, okay, these are the 9 values. And so now what is happening? So we are placing our filter here. So these, you can say that the red one is multiplied with 3, the green one is multiplied with 4, like that. Now, when you will place your filter here, the same red one, which was earlier multiplied with 3, that is 4. So red means here we are saying that some weight, right? So the same weight is, which was when my filter was at this position, this weight was multiplied with 3. Now the same weight is multiplied with 4, right? So that is what is there, right? So this is how we generate the new neuron over there. And this is the example of weight sharing, right? So we may think of convolutional layer as a hidden layer in which various inputs, they share the single weight parameter. So whenever you are going to place, because this filter, right, it is having these 9 coefficient, and whenever you are going to place it here, that pixel where you are placing this part of the filter will get this weight only, right? So that is what we are doing here, weight sharing. So as I already told you that we are going to get 3D outputs of depth D when we are using D different filters. So altogether, we'll say that our weights are here 4-dimensional. How this 4-dimensional? See this output depth, then your input depth, and your kernel height, the height of the filter and width of the filter, right? Right now, I showed you some examples where our kernel was 3 cross 3. So now let us come to the concept of feature maps, right? So what will happen when we are going, let us say this is my image, right? 3 channels. So 3 copies of the filter. Let us say I have chosen 2 filters I'm choosing here. So this is the first filter. I took 3 copies of the filter. I did this process, like this filter is moved over here. This filter moved over here. This filter moved over here. Then we added it, and then bias is added, and that is how we get this value, right? So what is this called? This is nothing but a feature map, right? So when you use this filter, convolve this input with this filter, this is your feature map, right? So because here we are using 2 filters, so we are getting 2 feature maps. So that is what we got here also. So this is the output of one the filter, and that is your feature map. So here you are using, let us say, D filter, so you will get D feature maps, right? So this is one example with 2 feature maps. Now it comes activation maps. So what happens? An activation function is actually applied on all entries of this feature map to get the activation map. Why? Because what happens here? Because the real life problems, when we say our real world is non-linear, right? It is not that simple linear, right? So our purpose is to introduce till now this convolution is a linear process, right? Multiplication, addition, so it is a linear process. So why we want this activation function to be introduced here? So that we can introduce some non-linearity in our convolutional network, right? And so here there are many activation functions. Your sigmoid is one of them. Today I will tell you about ReLU. We'll talk about it later. So now filters as activation map. So here what is happening? You have chosen so because your image is having 3 channels, so your filter is also having depth 3, right? And so you're convolving over all spatial locations to get feature map, and then on that feature map you are applying activation function on each entry, right? So that you will get the activation. So till now I told you to get feature map. Now on this each entry of this feature map, right, you are going to apply activation map, sigmoid, ReLU, whatever, and then you will get the activation map, right? So now, and this process will be repeated for each filter. So let us say filter 1, filter 2, like that, okay? So now let us say we take example, let's say, because I told you that our convolutional layer, it may having many filters, right? So let us say our convolutional layer has 6 filters. 6 filters, each of size 5 cross 5. So what will happen? Corresponding to these 5 cross 5 filter, because my depth is 3, so I will create this 5 cross 5 cross 3, and then I will get corresponding to one filter, I will get one activation map. Now here we are having 6 filters, so we will get 6 activation maps, right? So what happens that when we are keeping it, when we are having, this is our input image 32 cross 32, and then when we are using it, then these 6 5 cross 5 filters, we are getting a new image of size 28 cross 22, right? And depth is 6. So now let us talk about activation map. So activation function is, as I told you, is applied to each feature map entry. So this is the example here. So here you can see this is my ReLU activation function. And then here you can see this is again your picture. This is your filter. Now the filter maps. Now at each location, right, at each position, you are applying this activation function. See this, right? So each position here, that is representing this, right? And you are applying here, let us say, ReLU function, and that is how you will get the activation function, right? This is the example. So here you can see that. So if we talk about ReLU function, what is the output? Output is the maximum. So either 0 or input, whichever is higher. Maximum, that is the output. So if this is my feature map, right, then corresponding to this feature map, we are going to get this activation map, right? So this is there. So this is what we mean by activation map. Now, when we say that convolutional layers, then there are many such layers, right? So CNN is a sequence of convolutional layers, right? Which is interspersed with activation functions. And maybe later on, we will talk about pooling layers and all. So here you can see that our first convolutional layer that is having 6 filters, right? Of size 5 cross 5. And here the activation function is rel. Now the next, see here, the next convolutional layer is using 10 such filters, right, of size 5 cross 5. Now here you can see that important thing is there, this depth here, right? So here what is happening when you start convolution, so your picture is 32 cross 32 cross 3, so depth is 3. So when you are using these filters 5 cross 5, you are making depth as 3, because every plane, right, has to be, this convolution has to be done, and then as I showed you, the addition operation will be done. Now when you are going to apply this convolutional layer, because this convolution layer is having 6 filters, right? So corresponding to this image, I will get 6 planes, right? 6 activation maps. Okay. So my image is, and each activation map is of size 28 cross 28. So 28 cross 28 and 6 such activation maps. Now, next is what? When we apply it on, now my depth is 6. So when I am taking my filter, I am extending it to depth 6. And now we are having 10 filters, right? So the output volume will be having depth 10, right? This is how we are going to proceed. And here, if you have noticed, then see the input image size was 32 cross 32. Then after first convolutional layer, it becomes 28 cross 28. Then second convolutional layer, it becomes 24 cross 24. So why so? We will talk about it, right? So right now we can say that, okay, let us say my convolutional layer is using 32 filters, each of size, let us say 5 cross 5, right? So 5 cross 5 and the depth is 3. So you can see that, okay, these are my filters, and these are my 32 filters which are being used, and corresponding to each filter, we are going to generate one activation map, right? So corresponding to this, as I told you, this is a 3D volume, right? So how this 3D volume is generated? Here, see the response of first filter. So first activation map, right? This is your first activation map. Now let us say fourth filter, right? So fourth layer, right? Similarly, let us say this 30 seconds. So that will give you the last layer here, right? So that is how the activation maps are being generated, right? See, filters are taken square size, so that we can remember here, we want to have a clear center of the pixel, because if you see that we are placing when we are applying convolution, if you remember, I told you that we are placing filter on the image, the response is generated corresponding to the pixel where center of the filter is being placed, right? So we want a clear center, so these filters are square and also of odd sizes. So these are some examples of activation map, because our group is working on ophthalmological diseases also. So these are some activation map generated for that. And again, because of the time, I need to rush through a bit. Yeah. So now come to this, we have used, you just saw in the previous, I showed you that we have used 32 filters, and each filter gave me one depth slide, right? Or you can say one activation map. But if you observe that some activation maps are giving us almost same pattern, right? So it means that we are having some, if some filters are giving us same information, right? So almost same information, why we keep all those, right? So just see here. So number of filters in a single convolution layer are chosen. Remember, this is again a parameter which you have to choose. So number of filters in a single convolution layers are chosen by the user, right? And this depends upon the application as well as input data, right? So basically we choose a good number of features so that we can extract maximum number of features. So again, the question comes, I gave you answer. Now I hope you know the answer. What we are learning here, we are learning filters here, right? Filter coefficient. So in the beginning, we don't know filter. We just give random values to our filters, right? And during this training process, right, the filter coefficients are being learned. So you can see some demo also available here. And now we come to this convolution layer. And remember, in one of the picture, it was written stride 2. So what do we mean by stride? So what we are doing, basically during convolution, our filter slides over the picture. So see, now I have placed my filter here so that this, now this response which is produced, this is corresponding to this pixel. Right. So when I am placing my 3x3 filter here, the response is generated for this pixel. Remember, for this pixel, no response is generated because my center is not being placed here. And if I will place my filter by choosing center here, I mean, 1/3 part of my filter will go out of this image, and that is not. So we are placing filter on the picture so that the entire filter should be inside the image, right? Now I am going to move it. So what I did, I have moved it by 1 pixel, right? See, earlier this there, now this there. And again, so earlier I generated this response, now it is generating this response, and this is going on. So I'm moving this filter one pixel right, and now this is the last position I can move my filter here in this from left to right, because if I go further, then it will go outside. So I will go to the next line, right? So see, this is what is there. Sorry. So then I will go move to the one place down the this, right? This is how, and we will proceed. So here, when I'm moving my pixel by 1, right? Sorry, I'm moving my filter by 1 pixel, the stride is 1. Right. Now I can convolve it by choosing different stride also. For example, I may not want to shift just by 1 pixel. Here you can see I have shifted by 2 pixels. See here, I have shifted by 2 pixels, right? So every time I'm shifting by 2 pixels. Now I cannot move further because then my filter will go outside this, right? See, I'm telling you again and again, we are choosing odd size filters, right? 3x3, 5x5, like that. Okay, so, and if we will take, we can go for larger, like 7x7, 15x15, but that we don't go here because larger size filter means that more work is to be done in convolution, right? So here in the, we choose this small size filter, right? 3x3, 5x5, and later on I will tell you what happens in VGG. They say that, okay, response field is what, so whether we are going to get any benefit out of choosing large size filter. Important thing is to consider that these filters are square and of odd size, so that we are having clear center. Okay, so this is how my stride is there, right? So now what happens is that here, now if I will move it by 2 positions, again you can see that my filter will go out of it, right? So can't, it means that I cannot generate response of my filter for these pixels. Okay, similarly, what happens, I could not generate my response of this filter for these pixels, because when I placed my filter here, I get the response for this pixel, not for these pixels, right? And that is the reason, if you have observed that the size is becoming small, output size. See, when I chosen a filter with stride 1, this is the output size, but when the same filter, same 3x3 filter, let us say, and we are choosing this stride 2, now you can see the output is this. So decreasing. Okay. So now what happens that when you are convolving here, so here you just saw that when I'm saying, okay, my image size is 32x32 and I'm using this filter, now my output is 28x28, not 32x32. Now I hope you got the reason why we are having this, because see here, okay, just a minute. So see, if I'm going to choose here, so you can see that I'm placing my filter here, right? It means I'm not generating response for these pixels. Similarly, I'm not generating response for these pixels, right? So if I'm talking about 3x3 filter, right? And let us say stride is 1, then I am leaving, I'm not considering these pixels, right? The top row, bottom row, the leftmost column and the rightmost column. And that is why here you can see that okay, so here what happens, when we are using 5x5, then what will happen? The 2 columns left, 2 columns right, 2 rows top, 2 rows bottom. So the size is reduced by 2 from both the sides. So reduction is 4 there, right? So here you can say that our image from 32, it becomes 28. 28 cross 28, right? So this is how the size of the activation map is reducing. So now when you are using more and more filters, it means that the size is going to be reduced further. So our output volume is going to be reduced. So here you can see that, let us say I am saying that, okay, my picture is of size 256 cross 256 cross 3, and there are 8 filters, right? And each filter is of size 5 cross 5. So what will be the size of output volume? See here, when we are saying 5 cross 5 filter, so we will because the channel are 3, so we need to convert our filter also 5 cross 3, and then we are going to convolve it with each block, so that we are going to get just one output value, right? And when we are going to do this process, so what will happen? It is 5 cross 5, right? So the center comes, so the top 2 rows, if we start from here, let us say, and you are placing 5 cross 5 this thing here, okay? So what is mean that, okay, the top 2 rows, because the first center is placed here, the center of the, so it means that these top 2 rows and these left 2 columns, they are not participating. The same is true at the bottom also, at the right hand also. So that is how we can see that 2 and 2, right? So 4. So you can say that the size is 252. So you can see 5 cross 5, the center comes at the 3rd pixel. So 2 left and 2 right, 2 top, 2 bottom. So the reduction by 2 in both direction there. So that is how you get the picture of size 252 cross 252, right? And because we are having 8 filters, so 8, right? So how many activation maps you will get? 8 activation map, right? So the volume will be 252 cross 252 cross 8. So now we can get this, okay, with a simple thing, we can get this formula also. I mean, it is, for me, I don't go by the formula. For me, I mean, this understanding is enough. But still, for as a beginner, you can just go through this formula, right? Which will give you the dimension of output. Now, so here, that is what is happening. So 5 cross 5, see, from 32 cross 32, we are having this 28 cross 28, and from 28 cross 28, we are getting this 24 cross 24, right? So that is. So what happens if we are having more number of layers? So this size is going to be reduced, right? So, what does it mean? So basically what happens that, because we need, it means that not only the size is reducing, actually we are not considering some pixels in the picture, right? Those border pixels are not able to participate in the convolution process, right? So what is the common practice is to use zero padding, okay? So the 2 advantages are there of zero padding, that the dimension reduction is controlled and corner pixels will have better contribution. So here you can see that if I need this 3 cross 3 filter, now because I know that 3 cross 3 filter will give me a filter here, right? So what I did, I have appended these zeros here. So now my this corner pixel is also participating, okay? This is there. So with zero padding, so okay, now I need to skip a couple of things. So, okay, now let us say, let us take this example and then we'll move further. So let us say your image is of size 64 cross 64 cross 3. We are using 10 filters of size 5 cross 5. Padding is, because 5 cross 5, so padding must be of 2 and stride is 1. Now, what will be your output volume? See, output volume will be your, now you have done the padding, so no reduction in the output in the size right here. So this will be 64 cross 64, and then because we are using how many filters? 10 filters, right? So 64 cross 64 cross 10, right? So this will be the volume. Now how many parameters? Parameters, see, now each filter, what is there? 5 cross 5 cross 3, right? So 5 cross 5 cross 3 means this 75, right? And then plus 1 for bias. So how many parameters in a layer? 76 parameters in a layer. And then there are 10 layers, right? So total parameters to be learned, that is 760, right? So understand this. So now we are having, okay, now come to the fully connected layer. So because last layers will be fully connected layers, and here let us say input image size is this, then first of all you need to flatten it, and then here this, so this will become your dimension of input vector. And let us say if there are 10 neurons in the first hidden unit of your fully connected network, then what will happen? How many weights you need to learn? See, these many, all input vectors here are participating. No, in the convolution layer, what was happening? Sharing was done, right? Here, each position, right? We'll get the different weight, right? So, and then because there are 10 filters, so 10 bias, so total these many parameters, right? Now, if you would have been a convolutional layer in place of fully connected layer here, then the total training parameters, you can see they are much lesser than this, right? So this is, you can see the convolutional layer, and this is your fully connected layer, right? So each neuron basically looks at the full input volume, no when weight sharing is there. So here you can see this, okay, so let us say this is your filter 1 in the convolutional layer, so it is going to give you this, this is this value. Now, so this is what example I gave you earlier, weight sharing, the same thing here, right? So when you are multiplying it, now the same weights, right? So here you can see that you are not connecting to all of them, right? You are just connecting your filter to these 9 inputs, not all as it is done in the fully connected layer. So you are having less parameters, right? Fewer parameters. And now when you are moving your filter, then the same weights are being shared, right? So we can say that we are not changing those weights, right? The same filter coefficient. So these are the share weight, and we are having even fewer parameters. Okay, so this is how it gives. So this is the whole CNN architecture. Here you can see that the input image, and then we have convolution layer. We just talked about pooling layer. We are going to talk. So this we can have this convolution layers and pooling layers repeated many times, and finally we will flatten this all and we'll give it to fully connected feed forward network, and our classifier will classify this image as a cat, dog, whatever. So it is important to know pooling layer. So just give me 5 minutes to wind it up. So now because my images are large, right? So we want to compress these, right? So that we can manage the input output volume for different convolutional layers, right? So what pooling layers do, they make our representation smaller, and because of pooling layer, our output volumes become more manageable, right? And these pooling layers, they operate over each activation map independently. Now see, this is your volume, right? Output volume, okay? So 64 activation maps are here, right? And each activation map, so let us say, and as I told you, pooling, it will apply on each activation map. So we have taken one activation map here. Now, what is pooling? Basically, it is a downsampling, right? So your activation map becomes half of its size. And so now your activation, this output volume is reduced, right? So now how do we do this downsampling, right? Pooling. So there are 3 strategies: max pooling, average pooling, and min pooling. So max pooling, basically, let us say you have divided this into sub images, right? So let us say we are saying we are having our 2x2 filter, right? So because we need to use this to do. So 2x2 filter means 4 pixels when you are going to place it there. And here we are taking stride as 2. So when we will place our 2x2 filter, these are, the filter will be placed here. Now the stride 2. So the next time filter will be placed here, and that is how. Now, so in the max pooling, what we do, we take the maximum value out of these 4, let us say. So out of these 4, which is the maximum? 3. Similarly here, 2. Now here it is 1. Here it is 4. So this is the result of max pooling, right? So here you can see that these larger inputs are there. So you are okay, each activation map here. So one activation map, 2x2, right? Your filter, and this stride is 2. So you are taking the maximum. So you can see 9 here, 5 here, 8 here, like that, max pooling. Similarly, we have average pooling. So we are going to replace these 4 pixel by taking average of it, right? So simple average pooling, right? Now we have min pooling. Min pooling, we will take the minimum value, right? So just take the minimum. So what are the advantage of pooling? Pooling is basically a subsampling, and this with subsampling, you are not losing image information, right? And max pooling also performs as a noise, suppresses noise also. So we can say that max pooling performs a lot better than average pooling, you can say. So now the fully connected layer, because the final layers is fully connected. So for fully connected layer, we need to, so let us say after pooling, we got these there, right? So we just make it just flatten it, okay, and pass it to fully connected feed forward network. That is what is being shown here, right? So you can see that whatever is the so every stage, what is happening, you are doing convolution, max pooling, a new image, right? So every step you are going to get a new image, and finally you are flattening all data and passing it to feed forward network. Yeah, I will tell you at the end, right? So this is how you will get the now, just take this example of a convolutional neural network where you can see that the convolutional layers, right, ReLU activation function, and followed by, so see the pooling layers are inserted in between, right, and the final layer is your fully connected layer. So this is convolutional network to classify images as in these categories like truck, car, airplane, ship, horse, etc. Right. So here we are taking convolutional 3x3 convolutional filter, 10 such filters. Stride is 1, padding is 1. Okay, so let me tell you, somebody is having question on stride. So in the stride, what is happening? So first of all, you have placed your filter here. Now you are supposed to move your filter, right? So when we are moving our filter 1 pixel forward, the stride is 1. And we can move it more pixels forward also. So for example, let us say if I'm putting my I'm placing my, let us say, 3x3 filter here, right? Now, one thing is that I'm shifting it by 1 pixel, right? Another is there, I'm shifting it by 2 pixels, right? So filter is shifted by, here you saw just max, here it was there. So here you can see this 2x2 filters, right? So that is what I showed you just a minute. Just a minute. Yeah, this. See this. So here what is happening? You have placed your filter here. Now, if stride would have been 1, then you are supposed to place your filter like this. But here what is there? Stride is 2. So you have placed it there. Now leave 2 pixels and then again place your filter. Now leave 2 pixels and then again place. This is what do we mean by stride. Okay. No, because if you are going to increase the stride, the picture size is going to be reduced further. So it is not like you are removing, you are, making it a smaller size just by increasing the stride, because stride increasing means those pixels, if you're increasing stride, then many pixels in the picture are not able to participate, right? And even if you will take care of this zero padding, then also basically zero padding is there for, if you are taking too many zero padding, then it is actually going to affect the performance. Okay, so you can't compensate this with the stride, increasing the stride, right? So we are at the end, just okay. So what is the advantage of CNN in dealing with high dimensional data? First of all, we just saw that number of connections are reduced. There is parameter sharing, and the pooling layers are compressing output volume. We can work with inputs of variable size, right? So as a result, we are having much less number of parameters to be learned, right? So the deeper networks are possible. So what we are training in a CNN, remember here, so we are roughly speaking, we'll say that split and pre-process your data, choose your network architecture, right? And then initialize your weights, and find the learning rate and regularization strength, minimize the loss and monitor the progress. So basically we can say that you need to fiddle with many knobs there, right? So there are so many things to be fiddled there: network architecture, learning rate, regularization, loss function, weight initialization, update type, dropout, right? So many things, so many parameters you need to decide. Okay. So I will take this example, just to give me 2 to 3 minutes, and this will make everything clear. So here, see how this is the, so we now learn what is convolutional layer, what is ReLU, what is pooling layers. Now everything in just one architecture, what is happening? So let us say we have to train our CNN, and this here we want to train our CNN for 4 classes, right? Let us say these 4 classes are dog, cats, boat, and bird, right? So let us say, so what we want, let us say this image is of boat. So we want output label as what? See, we don't want as a dog, we don't want as a cat, we want as this 1 and 0. So this is what is our target vector. Okay. So what we'll do in the beginning, now listen carefully, because so many questions were there, how we are going to make use of filters and all. So in the beginning, what will happen? We are going to initialize all filters and parameters, weights, whatever you decide, with the random values. Okay. And then in the second step, your network takes the training image. So first of all, the network will take training image as an input. It will go through the forward propagation step, convolution. Here you can see that convolution, ReLU, pooling operations, right? And finally to the fully connected layer, right? And it will find the output probabilities for each class. For example, let us say at the training process, we got output probabilities as 0.3, 0.5, 0.2, oh, sorry, 0.2 इसको कर लीजिए, so 0.1. Okay, let us say we got these probabilities. It means that according to the probabilities we got, this will be a cat picture, but this is not the cat picture. So what is there? It means because, and why we are getting this output? Because our weights, the filter coefficients are not yet learned, right? We have randomly, see, I'm talking about training phase, right? So we have randomly assigned some weights to the filters, right? Filter coefficient, and that is why we are getting these probabilities, okay? So we need to train our network. How? So we need to find out the error, right? So third step, we need to calculate the error at the output layer, and that we will do it. We'll add it, find out the error for each class and add it there, and then use the back propagation, right? So that we are going to calculate the gradients of the error with respect to all weights here in the network. And we will be using gradient descent to update all filter values, right? So that we can minimize the output error. Okay. So it means that your weights are adjusted in proportion to their contribution in the total error, right? So what will happen? Let us say the next time, so when you are doing, the weights are updated. So the next time the same boat image will be there. So let us say this time my boat will be having probability, okay, 4, then 2.2, 0.2, and 0.2. So see, earlier the board possibility of board, like what was the score? 0.2. Now my score, because I did this back propagation, now my score is improved. So what will happen? This process, again we will calculate this error, and again we will perform this back propagation. And finally, so after repeating this step a couple of times, what will happen? That we will be generating the weight as, let us say, 0010, right? So when we will do it for this for the entire training set, then we will say that our convolutional neural network is trained, right? So remember, when we say that we have trained the convolutional network, it means that all the weights and parameters are now being optimized to correctly classify the images from the training set. And then we will come to the testing, right? So when a test image, a new image will be given, right, to this network, then the network will go through again the forward propagation step, and it will output the probability of each class. So for the new image, again we will get the probability for each class. And if our model is trained well, right, with the our training set was large enough, network has generalized well to new images, then the test image will be correctly categorized, right? So this is how you train your CNN, right? So we will talk about these CNN, some of these CNN architectures. There are several architecture in the tomorrow uh, lecture. And so now we know that everything is governed with the industry, and now we know that this deep learning, it is very much used with the industry. No need to tell you this, chat GPT and all are there. So used by all big shots there, right? And so these are some of the references I used. And so this is there, yeah. So I'm sorry, we have, I mean, I took your 10 minutes because, I mean, I knew that it will take some, I will go some out of time, because with the CNN, we have included deep neural networks as well as this uh, deep learning. So now if there are, okay, so I was taking in between questions, I believe. Yeah, definitely. See, when you are doing pooling, then definitely you are losing some information, but ultimately you need to manage the things. You can train your network so that this effect can be taken care. Yeah, this whole process, this all convolutional layers, pooling layers, activation functions, this all comes under the feature extraction. Okay, this question I've already answered. So effect of higher stride, as I told you, that the size of the output volume will decrease. Okay, so I believe. So if there is any question remains, then please drop it here, because from the chat, it seems I've taken. So we will talk more about object detection, don't worry, Rohan. So there are a couple of lectures on object detection. This time CNN basic function, this classification. Then we will gradually go for object detection. Okay, so I have taken questions from my side. Any question remains, then please let me know. So what is filter size? I told you, small size filters we use. It is not like you are fixing it up. Like different architectures you are choosing. This is what filter size. This is one of the parameter which you have to decide, right? What filter size you will choose. So usually we choose small filter sizes, not big ones. So 3, 5, 3 cross 3, 5 cross 5, like that. So okay, so no, it will not update during back propagation. It will not update stride or filter size that you have fixed. So that is not going to be changed, right? So you are only during back propagation when you have decided random, you have given random values to the filter coefficient, filter weights. So those weights will be updated, right? It is not like uh, during back propagation we are changing the size of the filter and all. Okay, parameter sharing. Just a minute. Yeah, the same thing here. I'm telling you this way, parameter sharing. See here. Oh, I'm sorry. Just a minute. See here, this parameter sharing. See what is happening here when you decide a filter, right? So let us say I decide a 3 cross 3 filter. Okay. So I am placing this filter here. Let us assume that the filter coefficients are represented by these different colors. Okay. Okay, so let us say first coefficient represented by red color, green color, blue color, like that. So this is your 9 coefficients, right? Now, when you are placing your filter here, then what happens that, see, red is multiplied with 3, 4, green is multiplied with 4, 7 is multiplied with blue, for example. Now, when you are going to have your stride as 1, your filter will move 1 pixel right. So now your filter will be placed here. So the red one, which is the first one, will be multiplied with 4. The green one will be multiplied with 7. The blue one will be multiplied with 8. So right now you can see that in the first go, red, green and blue, 3, 4 and 7. Now next time see this red, blue and green, this 4, 7 and 8. So that is how you will move, and the same parameters will be used for convolution process, right? That is weight share. Yeah, weights will definitely, when we are going to update the weights, and because of weights only the response is being generated. So you're changing the weights, obviously response is going to be changed, right? So I believe I must end here, because the next session is also about to start. So I will join tomorrow also. See, parameters, like here when we talk about weight sharing, the coefficients of the filters, right? That is what you are using for the repeatedly for the image pixels, right? And when we talk about, when we say about parameters, then in network, lot many parameters you need to decide. For example, how many filters, right? What is the stride? How you are going to do the pooling? How, I mean, all those things there. Weight sharing means that the same, the filter coefficients you are repeatedly using for different pixels in the picture. I hope it is clear. If not, I can repeat it also, no problem. Which pooling, as I told you, that usually this max pooling is giving you the good results. Okay, thank you. Thank you so much for taking so much interest and asking so many questions. Thank you. And let us meet in the next session, which is being taken by Samir, and where you will learn how to implement what I told you just now. Thank you. See you soon.